In this video, I would like to present a version of the Solow-Swan model in which it is augmented with automation technologies or robots in that sense. The sources on which this video is based are the papers by Lankish and co-authors 2019, How Can Robots Affect Wage Inequality, published in Economic Modeling. Then a paper of mine in Macroeconomic Dynamics, published in 2019, a note on the implications of automation for economic growth and the labor share. And the textbook treatment can again be found in chapter 4 of the book by me and David Bloom, Automation and its Macroeconomic Consequences, Theory, Evidence, and Social Impacts. First, we would like to know what the implications of the Solow-Swan model are for the factor income shares in an economy. And for this purpose, we again consider a Cobb-Douglas production function where aggregate output, which is equal to GDP of a country, is produced by using capital, so the machines, factory buildings, and so on, with an output elasticity of alpha, and workers, labor, L, with an output elasticity of 1 minus alpha. Now we already know we get per capita GDP by dividing by the population size or the number of workers, which is assumed to be the same in this basic version of the model. And per capita GDP is denoted with a lowercase y. And this is equal then to lowercase k, which is capital intensity to the power of alpha. Why is this the case? We see this immediately when we divide this expression here by L, then L drops out in here, and we have L to the power of alpha in the denominator. Now we can summarize k to the power of alpha and L to the power of alpha to have lowercase k to the power of alpha, because the definition of lowercase k is that it is aggregate capital divided by the number of workers, so the capital intensity. Now, in equilibrium of such a model with perfect competition, the factor rewards will be equal to the marginal product of the corresponding factor. So we will have that the capital rental rate, that's the interest rate plus the rate of depreciation, will be equal to the marginal product of the production factor capital. So that's the derivative of aggregate output with respect to capital. If we take this derivative, we see that alpha comes down from the exponent and we have to reduce the exponent by minus 1. L to the power of 1 minus alpha stays here unchanged. And now we can reformulate this by noting that L to the power of 1 minus alpha is the same of having L in the denominator raised to the power of alpha minus 1. So we can summarize uppercase k to the power of alpha minus 1 divided by uppercase L to the power of alpha minus 1 again into lowercase k to the power of alpha minus 1 because of the same definition as before, that lowercase k is the capital intensity. Well, and this is the same basically as having alpha times output per capita from here divided by the capital intensity, because you see, if you compute this here, k to the power of alpha divided by k, then we would be here again with k to the power of alpha minus 1. And a similar argument can be made with respect to the wage rate. The wage rate will be the marginal product of the production factor labor, so it's the derivative of output with respect to labor input. If we take this derivative, what we get is that 1 minus alpha comes down from the exponent, and we have to reduce this exponent by minus 1, so this minus 1 here drops out and we have minus alpha left here, and k to the power of alpha stays unchanged. Again, we can rearrange this by noting that this whole expression here is the same as k divided by L to the power of alpha, and aggregate k divided by aggregate L to the power of alpha is nothing else than the capital intensity to the power of alpha. Now, by the definition, or by this result that we have here for per capita output, if we plug this in, we get that the wage rate is equal to 1 minus alpha times y. Now we can compute the factor income shares in the standard Solow-Swan model rather easily, because by definition, capital income is the capital rental rate times the capital stock of an economy, and the capital income share is then the capital income divided by total income in the economy, so total output, GDP. Now we can see that if we divide the numerator and the denominator by the number of workers or the population size in the economy, then nothing actually changes because this just cancels out. So we can write this expression here also in terms of lowercase letters, where we would have the capital in density instead of aggregate capital in the numerator, and per capita GDP instead of aggregate GDP in the denominator. And now we can just plug in what we know from the previous slide, namely the expression for the capital rental rate. So we can plug this in here in this expression. And what we then get is alpha times y times k in the numerator divided by k times y in the denominator. And of course, everything cancels out here and only alpha remains. And alpha is a constant parameter. So this would imply that the Solow-Swan model predicts a constant capital income share. Now we can already guess what this implies for the labor income share. If the capital share is constant and we only have two types of factor inputs, then the other factor input would also stay constant. And we see this again if we do a similar calculation. We compute the labor income share, which is labor income. Labor income in turn is the wage rate multiplied by the number of workers. So that's the total wage bill. We divide it by total income, GDP, and get kind of the expression that we have here, because again we can divide the numerator and the denominator by L, then L drops out in the numerator, and in the denominator we would have per capita GDP, and then we plug in the expression that we had on the previous slide for the wage rate. So this expression here, we plug it into the numerator, and then per capita GDP drops out, and what remains is 1 minus alpha. So the labor income share would be 1 minus alpha. So the basic Solow-Swan model without automation would imply that the capital income share and the labor income share are always constant, irrespective of what happens in the model, irrespective of whether we are in the long run steady state or in the transition phase. It doesn't matter, capital and labor income shares are constant. Now for the United States, this parameter has been estimated to be around 1/3 until about the late 1970s, beginning late 1980s. So until then, for a century or so, the capital income share was indeed constant and the labor income share was also indeed constant. So the estimate that is usually used in the literature for alpha is therefore 1/3, and for 1 minus alpha, 2/3. However, since the 1980s, this has changed because the capital income share has increased in the United States and in many other countries as well, and the labor income share has correspondingly decreased. And now it's about 0.4, the capital income share, and the labor share is 0.6, so it has decreased by about 5 to 6 percentage points. Now what we've seen on the previous slide is that the traditional Solow-Swan model cannot explain what happened since the 1980s, when the capital income share increased and the labor income share decreased. Now, if we augment the Solow-Swan model with a new production factor automation, we will see that this augmented model can explain this decrease in the labor income share and the increase in the capital income share. To this end, we now assume that production follows a Cobb-Douglas production function again, but now with an additional production factor, namely automation capital or robots. And they are assumed to be perfect substitutes for workers here in this production function. And this is kind of the strict interpretation of automation, that a robot is capable of perfectly substituting a worker. Now, this has important and interesting implications, because automation capital here is by its definition capital, so the income that it generates goes to the capital owners that invest in automation capital, and it's an accumulable production factor. However, in the production process itself, it works as if it was labor, and it's a perfect substitute for workers, so it's actually in a perfect competition with workers. And we will see the implications that this has with respect to the labor share. And we will also see that this has implications with respect to the prediction of long-run economic growth, because in some sense we could now have increasing GDP by just accumulating capital and automation capital, and there would not be diminishing product with respect to capital when we consider both types of capital actually. Now, in this case, the factor rewards would again be given by the marginal product of the corresponding factor. So the wage rate is now again the derivative of the production function with respect to labor. And now we see something that is interesting. We know already, this is standard knowledge, that the wage rate increases with the accumulation of traditional capital. Why is this the case? Well, if we build more assembly lines, then we also need more workers to staff these assembly lines. So capital in the traditional form and labor are to some extent complementary. And if you accumulate capital, then also labor would be in more demand and the wages would rise. This is not the case, however, if you accumulate capital in the form of automation capital. In this case, the wage rate decreases. And the reason is exactly that these robots now are not complementary to workers, but they substitute for the workers on the assembly line. So if you accumulate more robots, then you can actually staff the assembly line with robots instead of workers. And therefore, we have this effect that P decreases the wage rate. And then we have the two rates of return for traditional capital and automation capital. And also here we see that with respect to traditional capital, we would have that if we accumulate traditional capital, then actually the rate of return on capital would decrease. This is simply a consequence of the diminishing marginal product of capital in the standard Solow-Swan model. However, when we consider automation, then we have that automation itself increases ceteris paribus the rate of return on traditional capital. So we actually have now a new production factor that can help to overcome the diminishing marginal product of capital. And as we will see later, this has the implication that in the automation-augmented Solow-Swan model, there is the possibility for perpetual long-run economic growth even without technological progress. And finally, we have the rate of return on robots here, on automation capital. That's the derivative of the production function with respect to P. And now this is the same as the wage rate, which is also not surprising because workers and robots are perfect substitutes. Now, what does the presence of automation imply for the factor income shares? To this end, we first compute aggregate labor income, which is the wage rate multiplied by the number of workers in the economy. So we plug in the wage rate from the previous slide and multiply by the number of workers here. And if we want to compute the labor income share, then we have to divide aggregate labor income, so the total wage bill, by aggregate GDP or aggregate income. So we see we can plug this expression in here for W times L in the numerator. So that's just that we have the denominator here now written in the numerator with minus alpha instead. And here we have GDP, so the production function actually. And now we can see that a lot here cancels out. And what remains on the right-hand side is actually 1 minus alpha times the number of workers divided by the number of workers plus the number of robots actually. Now we see that this automation-augmented Solow model does not feature a constant labor income share. Instead, the labor income share depends on the number of robots that we have in the economy. Now, as long as we don't have the possibility for automation, the number of robots would be 0. Then L would cancel out and the labor income share would be constant and equal to 1 minus alpha as in the standard Solow-Swan model. And therefore, correspondingly, the capital income share would be alpha. However, once we accumulate robots and once automation sets in, the labor income share would start to decrease. Now, this is basically what we observed since the 1980s, when automation became basically possible. So the robot stock was still negligible at the beginning, but it started to accumulate slowly, and this would imply a decreasing labor income share. So therefore, from this perspective, the automation-augmented Solow-Swan model is able to explain a declining labor income share. Now, what about the possibility for long-run economic growth in the automation-augmented Solow model? We already know that the standard Solow-Swan model implies that the economy stagnates in the long run if there is no technological progress. However, automation changes quite a bit in the model, as we've already seen, And we will now show formally that automation actually implies that the possibility emerges for long-run economic growth even in the absence of technological progress. To show this formally, we can basically go along two different ways. So we can assume that there are rational investors making rational investment decisions in automation capital versus traditional capital. Or we could assume, just consistent with the standard Solow-Swan framework, that all investment decisions are exogenous and assume that a constant share of investment is made in traditional capital and therefore a constant share in automation capital. The good thing is that it has no consequences for the results that we are interested in. They would be the same irrespective of which of these two ways of modeling it we choose. If we choose to feature rational investors, then we have in equilibrium that the rate of return on traditional capital and the rate of return on automation capital, they have to be equal, because otherwise rational investors would not invest in the form of capital that delivers a lower rate of return. And that implies, if we assume that both capital stocks have the same rate of depreciation, that also the interest rate of these two forms of capital would be the same. Now, if we use this and we set this expression equal to this expression now, we can then isolate actually P as a function of K. So we can express the stock of robots in the economy as a function of the stock of traditional capital and the number of workers. And this is easily done by reformulating, and we would get this expression here, where we see that the robot stock would increase in the traditional capital stock. The reason is clear. If we have more assembly lines and more production facilities, then we need to staff them somehow, and we can do this by using robots. And therefore, if we have more of this capital, ceteris paribus, for a constant amount of workers, we would have in equilibrium more robots. And we see that the number of robots decreases ceteris paribus in the number of workers that we have in the economy. And also this is perfectly intuitive, because if there are more workers, there is less need for automation actually. So in a country where labor is abundant, you have lots of unemployment or whatever, the wages would be comparatively low, and the pressure for automation would correspondingly be lower. Now we have expressed automation capital as a function of traditional capital and labor. Now we can plug this into the production function that we had at the beginning with automation capital. And if we do this and simplify, then we would get final output as a function of the traditional capital stock. And everything else is substituted out actually. So workers and robots do not show up here. Instead, a constant shows up in front of capital. Now, this also implies, as we see here, capital does not have an exponent, or basically the exponent is equal to 1. So that implies that the marginal product of capital is in equilibrium, not diminishing. And the intuition behind this is exactly that we have automation capital at our disposal. So if the rate of return on traditional capital would shrink, we could just invest in robots, and that would prevent the rate of return from shrinking further. And we could just have a production process in which the assembly lines are staffed by robots, basically. And this could go on perpetually, basically, and lead to perpetual income increases. So the standard reason here is for this kind of a K structure of the aggregate production function, that the accumulation of robots prevents the marginal product of traditional capital from falling. Nevertheless, we also want to show this analytically, so we go through the next steps, although it's basically already clear from an intuitive perspective. But we want to derive the long-run growth rate of this economy in a steady state where there is the possibility for perpetual long-run growth. And to this end, we compute three expressions first. Per capita output, that's just the aggregate output divided by the number of workers. So we get per capita output, and we get here the capital intensity. Automation capital per capita is this expression here divided by the number of workers. So we get lowercase p, the number of robots per worker, as a function of the capital intensity minus 1 here, because we divide labor by L. And then we can compute the evolution of automation density, basically, if we define the number of robots per worker as automation density by taking the time derivative of p. Now, if we take the time derivative here, we have that on the right-hand side, this term is constant, so this drops out, and the only thing that also depends on time is k, so we would have the derivative of k with respect to time on the right-hand side. And now we need all these three expressions for solving the Solow model with automation on the next slide. Here we have the aggregate accumulation equation for this automation-augmented Solow-Swan model, where this is kind of analogous to the standard Solow-Swan model, except for the fact that we have two capital stocks here, traditional capital and automation capital. And therefore we have the accumulation of these two stocks, such that on the left-hand side we have the sum of the change in traditional capital and the change in automation capital. And this is now related to gross investment. Gross investment is again a fraction of total income, because individuals are again assumed to save a constant fraction of their income, and this is available for investment. And we also have to take into account that both capital stocks depreciate, and we assumed previously that both depreciate at the same rate, so we can write minus delta times k plus p here. Now, in an analogous way as we did it in the standard Solow-Swan model without technological progress, but also with technological progress, we can compute the changes in per capita capital actually by doing the corresponding calculations and reformulations. And in this case, what we would get is the change in traditional capital per worker plus the change in automation capital per worker is now related to gross investment per capita and depreciation and capital dilution. So here we allow for population growth, and therefore the population growth rate appears negatively here, because if you have faster population growth, it becomes more difficult to equip the workers with the same amount of capital as in case of a lower population growth rate. Now we have a differential equation, but in two unknowns, the traditional capital stock and the automation capital stock. And ideally, to solve the model, which is then easier, we would like to transform this into a differential equation in just one variable. But the good thing is that this is straightforward to do, because we already have the expressions of the previous slide. So we know that for the time derivative of automation per capita, we can plug in the expression that we have here. And here we only have capital, traditional capital per worker showing up on the right-hand side. So we can substitute this out. For per capita GDP, per capita income, we can plug in this expression here, which also only depends on capital per worker. And for this expression here, for automation per worker, we can plug in this expression here that also only depends on capital. And this allows us to derive the equation that we have down here, which is now a differential equation in just one variable, namely the capital stock per worker. Now it looks a bit awkward, but actually we can solve it. We would divide by k, rearrange terms, and note that, for example, this term here, minus 1 divided by k, actually vanishes if k increases, because it becomes smaller and smaller, and in the limit it vanishes. And this expression here, so if we put out 1 plus 1 minus alpha over alpha and multiply this with k dot, then this term is equal to 1 over alpha. And in this case, then we can derive the growth rate of traditional capital per capita, and this would be the expression that we have here. It would be equal again to gross investment minus depreciation minus capital dilution. But now we see, and this is the interesting thing, that capital accumulation does not necessarily slow down if we have accumulation of capital. In the traditional Solow-Swan model, we had capital on the right-hand side to the power of alpha. So if capital accumulates, the marginal product of capital decreases. And that was the reason for why the gross investment curve was concave. Now here this is not the case. We could in principle have the situation that gross investment is higher than depreciation and capital dilution, and this holds perpetually. And this would hold, for example, if the gross investment rate is rather high. In this case, we can get perpetual accumulation of capital per worker in the economy, and its accumulation would not cease, and therefore by implication, as we will see on the next slide, also growth of per capita GDP does not cease. Because we see from these expressions that we derived earlier that if we have perpetual capital accumulation, we also have perpetual accumulation in per capita terms of robots. And we also have perpetual growth in terms of per capita GDP. And that's exactly what we can show here, that the long run growth rate of the economy, if the saving rate is high enough such that gross investment exceeds depreciation and capital dilution, is perpetually positive. So we have positive long run economic growth. The growth rate of per capita capital, of per capita automation capital, and of per capita GDP is then given by this expression here. It's the gross investment, which is the saving rate multiplied by this parameter cluster here, minus depreciation and capital dilution. So that means automation overcomes the diminishing marginal product of the production factor capital in the standard Solow-Swan model when we allow it in this framework, and therefore perpetual long-run economic growth becomes possible in this automation-augmented Solow-Swan. Now, two remarks to that. First of all, if we would not have allowed for rational investors, but instead assumed a constant fraction of investment in traditional capital, and if we denote this fraction by SK, then the long run growth rate would just look like this. So it's basically the same, and the parameter alpha is the parameter SK, but since both alpha is between 0 and 1 and SK cannot be anything else than between 0 and 1 by definition because it's a share, the implications are the same for the long run economic growth rate. That's the first remark. And the second remark is that, of course, we could have the situation that the saving rate is rather low as compared to the rate of depreciation and the rate of population growth. And in this case, the right-hand side could turn negative or zero. And in this case, we would indeed have a stagnation steady state as in the standard Solow-Swan model. So the economy would not grow in the steady state. If the right-hand side is negative, we would even converge to a situation where the economy would cease to exist at some point. Now we've seen that the automation-augmented Solow-Swan model can explain some interesting aspects. So we would have that the declining labor income share that we observed since the 1980s could to some extent be explained by automation and by the perfect competition of automation capital with workers. And we have the situation that there is the possibility for perpetual long-run economic growth that is driven by automation for certain parameter constellations. Now the question is, can we also say something with respect to inequality dynamics? And yes, we can if we generalize the production function to account for skilled and unskilled labor. So now we use a CES production function where we have skilled and unskilled workers, and we assume that robots are a perfect substitute for unskilled workers. So they can do the same tasks on an assembly line, for example, but not for high-skilled workers. So high-skilled workers, for example, in management or in or scientists and engineers and so on, cannot be perfectly substituted by automation capital in this setting. Nevertheless, the elasticity of substitution between skilled workers and unskilled workers is determined by gamma. And what we allow for is an imperfect substitutability between robots and high-skilled workers. So due to this structure here, we would still have an imperfect substitutability between these two production factors. Now, gamma would be in a range reasonably where high-skilled and low-skilled workers are imperfect substitutes, but they are still gross substitutes. So the tasks performed by low-skilled workers can be performed by high-skilled workers and vice versa. Not in the perfectly, there would be not a perfect substitution, but in principle it can be done. So this is the reasonable parameter range that we assume for gamma. And capital is just, again, the traditional capital, and we have the output elasticity alpha and for capital and 1 minus alpha for labor. Now we can compute again wages of skilled workers and wages of unskilled workers as the marginal product of the corresponding production factor. And what we would see then is again that the automation capital basically shows up in these expressions. So automation capital shows up in the wages of high-skilled workers and also in the wages of low-skilled workers. And if we divide now the wages of high-skilled workers and the wages of low-skilled workers, a lot drops out again. But what we would see is that this ratio would increase with automation. So if we have the accumulation of automation capital, then the ratio of skilled wages to unskilled wages goes up. And this is basically nothing else than the skill premium. And the skill premium has also been rising over the last decades quite a bit, and automation again can explain parts of these increases as we see here. So as automation capital is accumulated, the skill premium would increase. And of course, this holds only as long as gamma is smaller than 1. And as gamma that is smaller than 1 exactly implies that low-skilled and high-skilled workers are gross substitutes. So to summarize, this extension of the model would imply that the skill premium rises with automation, and this is consistent with the experience since the 1980s. Overall, we can now summarize that the Solow-Swan model with automation implies that there is the possibility for perpetual economic growth even in the absence of technological progress. The model can also explain the decrease in the labor income share that we have observed since the 1980s, or at least contribute to an explanation for this decrease. And an extension of this model can basically explain or also again contribute to an explanation of the rising skill premium since the 1980s, and this would also be driven to some extent by automation. Thank you again for your attention.